Right now, 33.8 billion light-years away, there is a galaxy. The James Webb Space Telescope first caught its faint trace of light on the 16th of May in the 2025, a single smudge buried deep inside an image of the dark. Hold one fact in your mind to feel that distance. The light arriving at Webb's mirror left that galaxy when the universe was only 280 million years old, roughly 2% of its current age. This light is older than the ground beneath you. It is older than the sun that warms it. It has been falling toward us, unbroken, for almost the entire history of everything. That alone would be remarkable. A galaxy caught so close to the beginning that the cosmos had barely drawn its first breath. But the distance is not the unsettling part. The age is not the unsettling part. The unsettling part is what was hidden inside the light. When astronomers spread that ancient glow into its separate colors, they found nitrogen. Not a faint smear of it, chemically complex nitrogen, the kind that should require many generations of massive stars to be born, burn through their fuel, and detonate as supernovae before it can exist at all. And there had not been enough time for that to happen. Not by a little, not by a margin you could quietly argue away, by a wide and impossible gap. The lead researcher, working at the Massachusetts Institute of Technology, reached for a word that scientists almost never permit themselves. He called it a cosmic miracle. And here is what most people get wrong about that phrase. They imagine he meant one lucky accident, a single beautiful object glimpsed at the very edge of what we can see. He did not. Because this galaxy is not alone. Sources like it appear to be more than 100 times more abundant than our most careful models ever predicted they could be. Not slightly more common, more than 100-fold. Consider what this means. The observable universe stretches roughly 46.5 billion light-years in every direction you could ever choose to look. 93 billion light-years from one far edge to the other. And out near the farthest boundary of that vast bubble, inside the oldest light we are able to gather, the universe is sending back a message. The message does not match the story we have been telling ourselves about how galaxies are built. It does not fail to match slightly. It does not fail at the edges. It fails at the foundation. For a century we have carried a calm and confident picture of the early cosmos. A slow, patient assembly. Small things first, then larger things, gathering across hundreds of millions of years like sediment settling on the floor of a quiet river. Webb was built, in part, to watch that gentle process unfold, and to confirm what we already believed. Instead, it keeps finding the wrong thing, in the wrong place, at the wrong time. Galaxies too massive, chemistry too rich, structures too bright, too numerous, and far too soon. The telescope is not broken. The numbers have been checked and rechecked and confirmed by other observatories standing on the far side of the world. The edge of the universe is simply refusing to behave. If you find something strangely calming in that idea, a slow and careful walk to the absolute limit of what human beings can see, the kind of quiet deep dive you can let yourself drift away inside, do me a small favor and tap the like button and subscribe. It genuinely helps this channel keep growing, and it lets me keep making these long journeys into the dark for you. There is nothing here that needs to be solved before morning. Get comfortable. Let's begin. To understand why the farthest light in the sky is quietly breaking our best theories, we have to begin much closer to home. We have to begin with the machine that found it, and with the strange and stubborn problem of how you build an eye capable of looking almost all the way back to the start of time. The machine has a name, and it has a birthday. On the morning of December 25th, 2021, while much of the world slept or sat quietly with family, an Ariane 5 rocket stood waiting on a launch pad at the edge of a rainforest in Kourou, French Guiana. Folded inside its nose cone, packed away like a piece of impossibly delicate origami, was the most ambitious scientific instrument human beings had ever tried to fly. It was not built to study the planets next door. It was built to look backward, Not backward in space, but backward in time, almost all the way to the beginning of everything. That distinction is worth sitting with for a moment, because it changes how you understand the whole project. When the James Webb Space Telescope opens its eye and stares into the dark, it is not seeing the universe as it is now. It is seeing the universe as it once was. The light arriving at its mirror left its source so long ago that the galaxies that sent it may no longer exist in the form we observe. We are not watching the cosmos, we are reading its memory. To do that, the engineers faced a problem that had no easy answer. The light they wanted to catch was unimaginably faint and unimaginably old, and it had been stretched and reddened by the long journey across an expanding universe. To gather enough of it, you need a very large eye. The wider the mirror, the more ancient light it can scoop out of the darkness. So they built a mirror 6.5 meters across, roughly 21 feet from edge to edge, far too large to fit inside any rocket ever made. The solution was as elegant as it was nerve-wracking. Rather than carve a single enormous disc of glass, the engineers built the mirror out of 18 separate hexagonal segments, each one coated in a microscopically thin layer of pure gold, each one mounted on a frame that could fold inward for launch and then unfold in space like the petals of a flower. Gold is not used for beauty. It is used because gold reflects infrared light with extraordinary efficiency, and infrared is precisely the kind of light these ancient galaxies arrive as. Together, those 18 segments form a single curved surface with about 25 square meters of light collecting area. To understand why that number matters, you only need one comparison. For more than 30 years, the great eye in the sky belonged to the Hubble Space Telescope, and Hubble's mirror measured 2.4 meters across. Webb's gathering area is roughly 6 times larger. That is not a small refinement. That is the difference between glimpsing the faintest smudge at the edge of the visible and resolving it into something you can actually measure. Hubble showed us the universe was deeper than we imagined. Webb was built to reach the parts of that depth Hubble could only hint at. But size alone was never going to be enough. There was a second problem, and it was, in its own way, far stranger than the first. The telescope was designed to see in infrared light, which is to say, the light of heat. Everything warm glows in the infrared. Your body glows. The walls around you glow. The earth glows, and the sun glows, and the moon glows. And here is the cruel difficulty at the heart of the whole design. A telescope built to detect the faint heat of the early universe would be utterly blinded by its own warmth. It would be like trying to photograph a single candle flame while standing inside a furnace. So the engineers did something that sounds almost paradoxical. They built a telescope that has to be colder than almost anything around it. Not pleasantly cold, not refrigerator cold. The James Webb Space Telescope must be kept below 50 Kelvin, which is roughly negative 223 degrees Celsius, or about negative 370 degrees Fahrenheit. At that temperature, the instrument's own infrared glow falls quiet enough that the ancient light it hunts can finally be heard above the noise. Achieving that cold in the harsh sunlight of space required one of the most beautiful pieces of engineering ever flown. Beneath the mirror unfolds a sunshield made of 5 separate layers, each one thinner than a human hair, each one stretched taut and held apart from the others by a precise gap of vacuum. The sun beats against the first layer with brutal heat. By the time that heat works its way through all 5 layers, almost none of it remains. One side of the telescope can sit at temperatures hot enough to cook, while the other side, the side that does the looking, sits in a cold so deep it would freeze the breath in your lungs in an instant. The sunshield does not merely block the sun, it blocks the heat of the sun, the earth and the moon all at once, holding the delicate side in permanent, perfect shade. This is the quiet genius of the whole machine. It does not fight the heat of the universe, it hides from it, and to hide properly, it had to travel somewhere very specific, somewhere far from the warm bustle of Earth. After launch, the folded telescope did not settle into orbit around our planet the way Hubble does. It kept going. For weeks it drifted outward, slowly unfolding its mirror and stretching out its sunshield in a sequence of hundreds of separate movements, any one of which, had it failed, would have ended the mission. In January of 2022, it arrived at its destination, a point in space about 1.5 million kilometers from Earth, roughly 4 times farther than the Moon. That point has a name. It is called the second Lagrange point, often written simply as L2, and it is one of a handful of special locations where the gravity of the Sun and the gravity of the Earth combine in such a way that a small object can hold its position with very little effort. Consider what that means. The telescope does not orbit the Earth, it orbits the Sun in lockstep with our planet, always staying on Earth's night side, always keeping the Sun, the Earth and the Moon clustered together behind its sunshield. It found the one address in the inner solar system where it could turn its back on every source of heat at the same time. From there, with its mirror cold and its eye open, it could finally begin to look, and what it looked at was not nearby. To grasp the scale of the territory this telescope was built to survey, you have to let go of a number that feels intuitive and accept one that does not. The universe is about 13.8 billion years old. It would seem to follow that the farthest thing we could ever see is 13.8 billion light years away, since nothing could have sent its light to us across a greater distance in the time available. That reasoning is sensible. It is also wrong. The reason it is wrong is that space itself has been stretching the entire time the light has been traveling. While a beam of ancient light made its long crawl toward us, the very fabric it moved through was expanding, carrying its point of origin farther and farther away. So the objects whose light we now catch are no longer where they were when they emitted it. They have been swept outward by the expansion of the cosmos. When you account for that stretching, the true reach of what we call the observable universe extends not 13.8 billion light years, but roughly 46.5 billion light years in every direction we choose to look. That gives the whole observable sphere a diameter of about 93 billion light years. This is the arena, a bubble of visible cosmos 93 billion light years across, every point on its distant surface showing us not a place but a moment. The deep past frozen in arriving light. The James Webb Space Telescope was built to push its gaze as close to the outer edge of that bubble as physics will allow, to the faint and reddened glow of the first structures that ever formed, in the era when the universe was young and the very first galaxies were just beginning to switch on. To carry out that search in an organized way, astronomers designed a dedicated campaign, a deliberate program of long, patient stares into carefully chosen patches of sky. One of the most important of these is the JWEST Advanced Deep Extragalactic Survey, known by the shorter name JADES. It was not built to find one famous object. It was built to map the faint and distant population of early galaxies systematically, to stare long enough and deep enough that the smudges Hubble could never resolve would finally separate into measurable points of light, each one carrying a number that tells us how far away it sits, and therefore how far back in time we are seeing it. And this is where the story stops being about engineering and starts becoming unsettling. Because the people who built this machine and the people who designed these surveys did so with a set of expectations. They knew, or believed they knew, what the early universe should look like. They had a theory, refined over decades, that predicted how quickly the first galaxies could form, how large they could grow, and how rare the truly massive ones should be in those first few 100 million years after the beginning. The telescope was meant to confirm that picture, to fill in its details, to show us the gentle, gradual assembly of structure from a smooth and simple early cosmos. What it found instead was something the theory did not allow. Consider what the theory actually predicted. The standard model of cosmology, refined patiently across more than half a century, describes a universe that begins smooth and simple and then assembles itself with enormous slowness. Structure does not arrive all at once. It accumulates, grain by grain, as gravity gathers thin gas into thicker gas, and thicker gas into the first faint knots of light. The earliest galaxies in this picture should be modest things. Not grand, not massive. They should be small, dim and rare, scattered like the first sparks in a fire that has only just begun to catch. This was never merely a guess. It was the direct consequence of everything we believed we understood about how matter behaves under gravity inside an expanding space. The numbers fell out of the equations, and the equations had been tested against the sky again and again. So the people who pointed this telescope toward the deep past did so expecting to watch creation proceed gently. They expected to see the universe being shy. What they were really doing, though they did not yet know it, was setting a trap for their own assumptions. To feel why this matters, you have to understand what it means to look far away. When you observe something distant in space, you are not seeing it as it is now. You are seeing the light that left it long ago. Light that has been crossing the emptiness for the entire span of its journey toward you. The farther away an object sits, the older the light and the deeper into the past you are looking. A telescope is therefore not only an instrument of distance, it is an instrument of time. To look toward the edge of the observable universe is to look at the universe when it was young, and the observable universe is larger than instinct expects. It extends roughly 46.5 billion light-years in every direction, a sphere some 93 billion light-years from one side to the other. Yet the universe itself is only about 13.8 billion years old. At first glance this seems impossible. Nothing travels faster than light, so how could we see things whose light would need far more than 13.8 billion years to reach us? The answer is not that light somehow cheated. The answer is that space itself has been stretching the entire time, carrying those distant regions ever farther from us, even as their ancient light crawled inward. This is the strange architecture of cosmic distance. The light that arrives today began its journey when the source was much closer. While that light travelled, the space between us swelled, and the source was swept outward to its present remoteness. So the number we report as a galaxy's distance is not a single fixed thing. It is a record of a journey through a growing cosmos. When a galaxy is described as sitting more than 30 billion light-years away, while being seen as it was only a few 100 million years after the beginning, both statements are true at once. The nearness belongs to the past, the vast distance belongs to now. Hold that against the scale of time, and the strangeness sharpens. The universe is roughly 13.8 billion years old. The galaxies at the very edge of the telescope's reach are being seen as they were less than 300 million years after the beginning. That is barely 2% of all the time that has passed since. Imagine compressing the entire history of the cosmos into a single year. On that calendar, these galaxies appear in the first days of January, when the fire of creation has scarcely cooled. They should be embers. They are bonfires. This is why the deepest galaxies are also the faintest. Their light has not only travelled almost the entire age of the universe, it has been thinned and dimmed and drawn out by the expansion of everything in between. To gather it at all requires patience measured not in minutes, but in hours of unbroken staring at a single dark patch of sky. The survey built to do exactly this was called the JADES program, the Deep Extragalactic Survey, designed to find and measure the first generations of galaxies. It was meant to be a careful census of the shy early cosmos. It became, instead, a catalogue of impossibilities. Because the theory was specific about what that census should reveal. In the first few 100 million years after the beginning, there had simply not been enough time. Not enough time for gas to cool. Not enough time for it to collapse into the first stars. Not enough time for generation after generation of those stars to be born, to burn, and to die. The early universe was supposed to be a nursery, holding small and simple things still waiting to grow. A massive, bright, chemically rich galaxy that early would be like finding a fully grown oak in soil that had only just been seeded. What the telescope saw in those first deep images did not match the nursery. The smudges resolved into galaxies that were too bright, too large, too mature for the age at which they were being observed. There were too many of them, and they carried the chemical fingerprints of stars that should not have had time to live and die yet. The instrument had been built to confirm a gentle story of slow assembly. It returned, almost immediately, a sky that contradicted that story at the most basic level. And the disagreement was not small. It was not a matter of a single galaxy being a little heavier than expected, or a little brighter, the kind of mismatch that careful revision can quietly absorb. The objects at the edge of the observable universe appear, by some estimates, more than 100 times more abundant than the standard model ever allowed for. Not a rounding error, not a footnote awaiting a minor correction, a gap of 2 full orders of magnitude between what the best theory of cosmic history predicts and what the most powerful telescope ever built actually shows us. This is the quiet crisis hiding inside the beautiful pictures. The public saw glittering galaxies and called them gorgeous, and they were. But the astronomers studying them saw something else underneath the beauty. They saw a number that should not exist, repeated across the sky, refusing to go away no matter how the data were checked. Every reasonable explanation was tested, every measurement was scrutinized for error, and still the early universe remained stubbornly, impossibly full of things that by every prediction had no business being there. So here is the crushing truth that the grounding leaves us with, the truth that everything after this must reckon with. We did not build the most expensive telescope in human history and carry it 1.5 million kilometers from Earth to be reassured. We built it expecting confirmation. What it handed back instead was a sky that does not obey our theory of how it came to be. To reckon with a sky like that, you first have to understand how we read it at all. Because the strangeness does not begin with what these galaxies are. It begins with how we know they are there in the first place. The light that finally reaches the telescope is not a photograph in any ordinary sense. It is a message that has been altered in transit, stretched and reddened by the journey itself. And learning to decode that alteration is the quiet foundation beneath every astonishing claim that follows. Consider what happens to sound. You have stood on a street and heard a siren shift as an ambulance raced past you. As it rushed toward you, the pitch climbed higher and thinner. As it pulled away, the pitch fell lower and rounder. Nothing changed inside the siren itself. What changed was the spacing of the waves reaching your ear, pressed together as the source approached, drawn apart as it fled. Light carries its information in a similar way, though for reasons far older and far stranger than a vehicle on a road. Light arrives to us as colour, and colour is simply wavelength. Blue light is made of short, tightly packed waves. Red light is made of longer, more widely spaced waves. When light from a distant galaxy travels toward us across the cosmos, those waves are stretched out along the way, shifted from the short blue end of the spectrum toward the long red end. Astronomers call this redshift. And the crucial point is what causes it. Not the galaxy fleeing through space the way the ambulance fled down the street. The space between us and that galaxy has itself been expanding the entire time the light was in flight. Picture a single wave of light drawn on the surface of a balloon. A simple ripple with crests and troughs spaced evenly along the rubber. Now imagine the balloon slowly inflating. It does not push the wave from one place to another. It expands the very fabric the wave is painted upon. The crests drift apart. The troughs widen. The ripple grows longer and lazier without ever sliding across the surface, simply because the surface beneath it grew. This is what happens to starlight crossing the cosmos. The wave is not pushed. The road it lies upon is lengthened underneath it, mile by mile, age by age. This is the mechanism that lets distance be read directly out of light. The more the universe expanded during a beam's long journey, the more its waves were stretched, and so the more redshifted it appears when it finally arrives. A small redshift means light from a relatively nearby galaxy that crossed a younger, smaller cosmos. A large redshift means light that set out when the universe was a tiny fraction of its present size. Light that has been riding the swell of expansion for almost the entire age of everything. Redshift, then, is a clock and a ruler fused into a single number. It tells you how far the light traveled and how long ago it left, both at the same time. This is why the numbers seem to break common sense. The universe is roughly 13.8 billion years old, yet the edge of what we can observe lies some 46.5 billion light years away in every direction. The reason is not that anything outran light. The reason is that while the light was crossing toward us, the space it had already traversed kept stretching behind it, carrying its origin point ever farther away. The light is ancient. The distance it now stands for is a distance that did not even exist when the journey began. Here is where the engineering meets the physics. Light that leaves a very early galaxy as visible or ultraviolet light, stretched across more than 13 billion years of expansion, does not arrive as visible light at all. By the time it reaches us, every wave has been pulled so far toward the red that it has slipped beyond the range our eyes can register, and beyond the range that earlier telescopes were built to capture. It arrives as infrared. It arrives as heat. This is the precise reason an instrument as celebrated as Hubble simply could not see the first galaxies. Not because Hubble was weak, not because it was poorly made, but because it was listening, so to speak, in the wrong language. The earliest light had been transposed into a key that Hubble was never designed to hear. Every major decision behind the new telescope flows from this single problem. Its detectors were tuned for the infrared. Its mirror was made enormous to gather the faint trickle of light that survives such a crossing. And it was carried far from Earth, wrapped in its great layered sunshield, and chilled to a brutal cold for one reason above all others. An instrument hunting for faint infrared light cannot be glowing with infrared light of its own. A warm telescope searching for ancient cosmic heat would be like trying to photograph a single candle while standing inside a furnace. The cold is not a luxury. The cold is the only condition under which the experiment can work at all. And so we come to the act of measurement itself, which is far slower and far more painstaking than the glittering images ever suggest. To merely photograph a faint smudge is not enough. A smudge could be a nearby object dressed in deceptive color. To truly know how far the light has traveled, astronomers must spread it out into a spectrum, splitting the combined beam into its individual wavelengths the way a glass prism fans white light into a rainbow. Within that spread, certain features appear, fingerprints left by specific chemical elements, sitting at wavelengths that physics has measured with exquisite precision in laboratories here on Earth. By seeing how far those fingerprints have shifted toward the red, the distance can be read with confidence rather than merely guessed. In January of 2024, that is exactly what the telescope did to a single faint object catalogued within a deep survey of one small patch of sky, a program known as the JWEST, Advanced Deep Extragalactic Survey. The near-infrared spectrograph aboard the telescope stared at that one smudge for 10 continuous hours, gathering its meager light almost particle by particle, building a spectrum detailed enough to trust. When the fingerprints were measured, the shift was staggering. The light carried a redshift of 14.32. A number like that is difficult to feel until it is translated. A redshift of 14.32 means the light reaching the detector left its galaxy when the universe was only a few 100 million years old, a thin sliver of its present age, less than 3% of the time that has passed since the beginning. It means the waves of that light had been stretched to roughly 15 times their original length during the long crossing, and it means a new record, because the same survey had only recently held the previous record with a different galaxy at a redshift of 13.2. The frontier was not advancing by accident. The telescope was pushing the edge of the visible past outward, confirmed object by confirmed object, each one deeper in time than the one before it. Consider what this means for the person quietly watching. The light that settled into that detector after 10 patient hours was older than the earth beneath your feet. It was older than the sun. It was older than nearly every atom arranged into the world you know. It began its journey when there were no planets, no rock, no carbon assembled into anything that could one day wonder about it, and it crossed an expanding darkness for almost the entire history of time before ending its travel inside a machine built by creatures who would not exist for billions of years after it first set out. You are not looking at that galaxy as it is. You may be looking at the ghost of something that lived and changed and scattered long before our solar system ever formed. This is the vertigo hidden inside the simple word distance. In everyday life, to see a thing is to know it is there. You look across a room and the chair exists in the very moment you perceive it. But across cosmic gulfs, sight and existence come apart from one another. To see across such a distance is not to witness the present, it is to receive the past, delivered impossibly late, a letter written by a sender who may have vanished ages ago. The galaxy the telescope shows you is a portrait of an infant, and that infant, if it survives at all, is now unimaginably changed and unimaginably far. This is the instrument we trusted to settle our deepest questions, a machine that does not show us the universe as it is, but as it once was, reaching back through stretched and reddened light toward the first faint fires of creation. We aimed it at the earliest, most pristine layer of the past we had ever been able to touch. We expected to find the simple, modest beginnings our theory had always promised. The standard model of cosmology, the framework astronomers call lambda cold dark matter, made a clear and humble prediction about what those first galaxies should be. Small, faint, sparse, barely begun. We expected to read, in that ancient light, the quiet opening pages of cosmic history, the gentle first chapter before complexity had any time to gather. What the spectrum revealed instead was something that prediction had left no room for at all. To understand the shape of that surprise, you first have to understand how a spectrum speaks. A spectrum is not a picture, it is a confession. When you spread the light of a galaxy out into its separate colors, the way a prism unbends a single sunbeam, you find dark lines and bright lines scattered through it like the bars of a code. Each line is a fingerprint left by a particular element. Hydrogen marks the light in one place, oxygen marks it in another. These positions are fixed. They are written into the structure of the atoms themselves, and they do not change from one side of the universe to the other. But the positions you observe do change, not because the atoms are different, because the light has traveled. As the universe expands, it carries galaxies apart from one another, and it stretches the light moving between them along the way. A wave that left its source as ultraviolet, tight and energetic, arrives at the telescope loosened and lengthened, slid down toward the red end of the spectrum and beyond it, out into the infrared where the human eye cannot follow. The fingerprints are still there. They have simply all moved in the same direction, by the same proportion, like a song transposed into a lower key. It is the same thing your ear notices when a siren drops in pitch as it recedes down a street. Measure how far the lines have shifted, and you have measured how much the universe has grown since that light began its journey. You have measured, in a single reading, both distance and time. This is why Webb was built to see in infrared, and it is the heart of why it can do what Hubble could not. The light from the first galaxies has been traveling for so long, through so much expansion, that it has been stretched almost past recognition. What began as the brilliant ultraviolet glow of young hot stars reaches our solar system shifted entirely out of visible light. To Hubble's eyes, tuned mostly to the colors we ourselves can see, these galaxies are not faint. They are simply absent. Their light has moved to a place Hubble was never designed to look. Webb was built precisely to look there. It was engineered, from its frozen mirror to its careful instruments, to catch the exact reddened, exhausted light that older telescopes let slip through their fingers. The instrument that performs this final reading is called the near-infrared spectrograph. To confirm a single galaxy at the edge of the known universe, it does not glance. It stares. In January of 2024, astronomers held the telescope steady on one faint smudge of light for 10 continuous hours, gathering photons one at a time, building the spectrum line by patient line until the fingerprints rose out of the noise. What they read was a redshift of 14.32. The light arriving at the mirror had been stretched to more than 15 times the wavelength at which it first left those distant stars. The galaxy, catalogued in the dry shorthand of astronomers as Jade's GSZ 140, was seen as it existed when the cosmos was only about 2% of its present age. It was, in that moment, the most distant object humanity had ever confirmed, and it had taken that title from a galaxy Webb itself had crowned only shortly before. The previous record holder, Jade's GSZ 130, sat at a redshift of 13.2, already almost unthinkably remote. Webb found something farther. This is the rhythm the telescope established, almost from the moment it opened its eyes. Each record stood for a season, not an era. Each impossible distance became within months the new ordinary, surpassed by something more impossible still. The machine kept reaching past its own reach, and every time it did, it was not merely nudging a number higher on a list. It was pushing the boundary of the visible past further back toward the beginning, into a stretch of time we had assumed would be thin, quiet, and almost empty. It helps here to sit for a moment with how such distances are even possible. The universe is 13.8 billion years old. Light travels at a fixed and finite speed. You might reasonably assume then that the farthest we could ever see is 13.8 billion light years, the distance light could cross in the universe's entire lifetime. But the observable universe reaches far beyond that. It extends roughly 46.5 billion light years in every direction, a span of some 93 billion light years from one edge to the other. The reason is the same mechanism that reddens the light. Space itself has been expanding the whole time that light was in flight. The galaxies that sent us their ancient glow have been carried ever farther away while their light crawled toward us, so that by the time it arrives, its source sits at a distance the light could never have crossed on its own. We are not seeing across a still room. We are seeing across a room that has been stretching the entire time the message was in transit. This is the framework the whole edifice rests upon. The standard model of cosmology, the one astronomers call lambda-cold dark matter. It is not a vague story. It is a precise mathematical machine, fed by decades of measurement, and it makes specific, testable predictions about how quickly structure could assemble in the young universe. Gas had to coal. The first stars had to ignite. Gravity had to gather those stars into clusters, and clusters into the first true galaxies, slowly, across many millions of years. The theory told us, in numbers rather than hopes, roughly how massive a galaxy could become by the time the universe was only a few 100 million years old. It told us how bright such a galaxy could be, how many we should expect to find, how rare the earliest light ought to be. Webb was, in a sense, the perfect examiner. It could read distance and time directly from stretched light, and chemistry directly from the fingerprints buried inside it. It was built to grade the theory's predictions against the universe's own confession. Consider what this means for the people who built their working lives around that theory. An astronomer does not simply learn the standard model. They live inside it. They spend years, sometimes decades, learning to think in its language, to feel in their bones what the early universe should look like, to predict before they observe, to sit in a darkened room and watch a spectrum resolve out of 10 hours of accumulated starlight, is to put that entire inner conviction on trial. The fingerprints either fall where your understanding says they must, or they fall somewhere else. And when they fall somewhere else, the cold, quiet feeling that follows is not excitement. Not at first. It is the vertigo of standing on ground you trusted and feeling it move beneath you. That is the strange honesty of this instrument. It does not argue. It does not theorize. It simply gathers the oldest light in creation, stretched and reddened across 13 billion years of expanding emptiness, and lays it down in front of us exactly as it is. The mechanism cannot be flattered and it cannot be talked out of what it sees. It reports the fingerprints, and the fingerprints report the truth. And in the first full readings it returned, in those patient lines pulled from the very edge of time, Something was already waiting, something no equation had asked for, and no astronomer had ever been trained to expect. The first thing it found arrived wearing a name that looks like a filing code, a survey label, a few quiet letters, and a number stitched onto the end of it. There is nothing in those characters to alarm you. They read like an entry in a ledger, a coordinate, a thing to be catalogued and shelved without a second thought. But the number at the end of that name was a redshift of 14.32, and a redshift is simply a measure of how far light has been stretched on its long way to us. The larger the number, the older and the more distant the light. And a redshift of 14.32 pointed to a galaxy seen as it existed only 290 million years after the Big Bang. That is roughly 2% of the universe's current age. Nearly all of cosmic history still lay ahead of it. This faint smudge was very nearly the first thing the cosmos had ever made. It is worth pausing on what 2% really means, because the mind slides off a fraction like that. Imagine compressing the entire history of the universe, all 13.8 billion years of it, down into a single calendar year. On that scale, the Big Bang happens in the first instant of the 1st of January. The Earth does not form until well into the autumn. Every human who has ever lived appears in the last few seconds before midnight, on the final night of December. And this galaxy, the one Webb had just pinned to the dark, would have formed in the opening week of that imaginary year. It is light from the infancy of everything. To look at it is to look at a time before stars had any company, before there were planets, before there was anyone to wonder where it all came from. In January of 2024, a team working with the James Webb telescope turned its spectrograph toward that smudge and simply held it there. Not for a moment, not for an hour. For 10 continuous hours, the instrument gathered the few faint photons that had survived a journey of more than 13 billion years, building the spectrum line by patient line. 10 hours of staring at a single point of ancient light, just to be certain. The longer it stared, the more the noise fell away and the truth emerged. When the spectrum finally resolved, the distance was confirmed beyond reasonable doubt. This was, at that moment, the most distant galaxy that humanity had ever measured with confidence. That alone would have been a triumph, a new record, a deeper reach into time than anyone had managed before. But the triumph was not the problem. The problem was what the galaxy turned out to contain. It stretched more than 1,600 light-years across, far too broad to be a single bright knot of freshly lit stars. It held a stellar mass of several 100 million times the mass of our Sun, and it was assembling new stars at a rate of roughly 22 times the mass of our Sun every single year. For an object this young, in a universe this new, those numbers did not fit any picture that anyone had drawn. They described not a faint first attempt at a galaxy, but something already substantial, already busy, already well along. Then came the detail that turned a puzzle into something colder. Buried within that hard-won light was the unmistakable signature of oxygen. Ionized oxygen, the most distant detection of that element ever made in the history of science. And oxygen is not something the universe is born holding. The Big Bang forged hydrogen and helium, and almost nothing heavier. Everything else, every atom that matters to a rock or a planet or a living body, had to be built afterward, inside stars. Consider where oxygen actually comes from. Every atom of it in existence was cooked in the searing core of a massive star, fused together over the star's lifetime, and then flung outward across space when that star tore itself apart in a supernova. There is no other factory. The oxygen in the air you are breathing was made this way, in stars that died before the sun was born. So to find oxygen already woven through a galaxy, only 290 million years after the beginning, is to find the evidence of a death. Not a single death, many of them. Consider what that truly requires. For oxygen to exist in that galaxy in the quantity Webb detected, stars had to form, live out their entire lives, and explode, scattering the heavier elements they had built, and not just one generation of them. To enrich a whole galaxy this thoroughly, Multiple generations of massive stars had to be born, burn through their fuel, and die in sequence, one wave after another, before the light we are now seeing ever departed. If the universe was only 290 million years old in this image, then the clock allotted for all of that creation and destruction was impossibly short. The cosmos had barely opened its eyes, and already it was littered with the ashes of stars that had lived and burned and gone. Kevin Heinlein, an astronomer at the University of Arizona, reached for an image to describe what this felt like to confront. He said it was like an anthropologist finding an enormous ancient city and seeing within its ruins the evidence of iPhones. The comparison is more exact than it first appears. The unsettling thing is not that the city is large, it is that the city is too advanced for its own age. You arrive expecting mud and stone, a few rough dwellings, the very first fumbling marks of settlement. Instead you find streets and machinery and a level of development that should have demanded ages the timeline simply cannot supply. That is the dissonance. The galaxy was not merely old. It was too finished, too mature, too chemically rich for the brief sliver of time it had been given to become anything at all. The honest, disciplined response to a result like this is doubt. Perhaps the instrument was mistaken. Perhaps the light had been misread, the distance overestimated, the signal quietly contaminated by something nearer and more ordinary masquerading as something ancient. Science earns its trust precisely by trying to break its own findings before anyone else can. And so the galaxy was examined again, this time by a different machine standing on a different continent. In March of 2025, a team led by the astronomer Carniani turned to Alma, a vast array of radio dishes spread across the high desert of Atacama in northern Chile, and searched for the same oxygen signature in a different band of light. They found it. Two independent observatories, built on different principles, looking through different windows, arrived at the same answer. The galaxy was as distant as claimed, and as enriched as feared. There was no comfortable error left to retreat into. And here is the part that lets the cold, quiet feelings settle in and stay. This galaxy was not a freak. It was not a single strange object that could be quietly set aside as an outlier and forgotten by morning. It was the clearest single example of a pattern the telescope kept returning, again and again, every time it pushed closer to the edge of its reach. The deeper Webb looked, the more it found structures that should not yet exist. Galaxies too large, arriving too soon, chemistry too complex, appearing far too early. The universe described by the standard models was supposed to begin slowly and gently, with small, dim clumps of gas gathering over hundreds of millions of unhurried years before anything deserved to be called a galaxy at all. What the instrument actually returned was a young cosmos already crowded with the grown, the heavy, and the finished. To understand why this is so deeply disturbing, it helps to step back from this one galaxy and look at what had come before it, because the first real warning had not arrived in 2024. It had arrived more than a year earlier, in a paper that used a single word no careful scientist ever reaches for without weighing the cost of it. The word was impossible, and the astronomer who chose it had not chosen it for drama, or for headlines, or for effect. His name was Ivo Labbé. He worked at the University of Melbourne on the far southern side of the world, far from the great observatories of the northern sky. In February of 2023, more than a year before that oxygen spectrum unsettled the team in Arizona, he and his colleagues published a paper in the journal Nature that would land like a stone dropped into still water. They had been studying some of the very first images Webb returned, and buried inside those images, in a small patch of sky no wider than a thumbnail held at arm's length, they had found 6 faint smudges of light that did not belong. 6. Not 1,000. Not 100. 6 faint objects, scattered across one of the deepest exposures the new telescope had taken. At first glance they were unremarkable, reddish, compact, easy to overlook. But when Labbé and his team measured how far away these 6 objects truly were, and then measured how much light each one was pouring out, the numbers did not add up to anything the standard picture of the cosmos could permit. These 6 galaxies existed between 500 and 800 million years after the Big Bang. By cosmic standards, this is the deep newborn dark. The universe at that age was a small fraction of its present size, still warm with the afterglow of its own birth, still busy assembling the very first generations of stars. According to every model astronomers had built over the previous half-century, galaxies at this age should be small. They should be faint. They should be ragged little knots of gas, only beginning the slow work of becoming something larger. That is not what Labbé found. Each of these 6 objects appeared to contain something on the order of 100 billion stars. Not 100,000, not 100 million, 100 billion. A number that matches almost exactly the entire stellar population of the Milky Way galaxy that surrounds you tonight. The same Milky Way that took more than 13 billion years to gather the stars wheeling silently above your roof. And here was its twin, its full-grown equal in mass, somehow already complete when the universe had lived through less than 1/20th of its current age. Consider what this means. It is the difference between watching a forest rise slowly over centuries and walking into a clearing to find ancient towering trees that were somehow planted yesterday. The mass was there, the stars were there, the time required to build them was not. Labbé chose his words with the care of a man who knew exactly how they would be read. "We just discovered the impossible," he said. "Impossibly early, impossibly massive galaxies." He did not say improbable. He did not say merely surprising. He reached past every softer word available to a careful scientist and selected the one that means cannot be. And he selected it knowing that if he was right, something fundamental in our account of how the cosmos assembles itself would have to be torn down and rebuilt from the ground up. To make the strangeness tangible, Labbé offered a comparison that has stayed with people ever since. Imagine, he said, an adult human being who weighs 100 kilograms but stands only 6 centimeters tall. Picture that for a moment. A full adult mass, the weight of a grown person, compressed into a body no taller than a human finger. That is the kind of contradiction these galaxies embodied. So much material, packed into so little room, arriving so impossibly soon. Everything about them was wrong in the same direction at once. Too heavy, too dense, too early. His co-author, Erica Nelson, working at the University of Colorado, described the experience of staring at the data as a kind of vertigo. These were not the faint expected smudges of a young universe. They were giants, fully formed, looking back out of the deepest past the telescope could reach. And the team understood almost immediately that they had not merely found something new. They had found something that the rules, as written, did not permit to exist. This is the disturbing reality of what Webb had begun to do. It was not adding interesting footnotes to a settled story. It was returning evidence that the story itself might be wrong in its opening chapters. Not wrong in the small details. Not wrong by a slight margin that careful adjustment could quietly repair. Wrong about the most basic question of all. The question of how quickly the first great structures could possibly come together out of the cooling dark. Now, science is built to doubt itself, and the doubt arrived quickly. Whenever a result threatens to overturn a foundation, the first and most important question is always whether the result is real. 6 faint red points of light at the edge of the observable universe leave enormous room for error. Perhaps the distances were wrong. Perhaps these objects were closer than they seemed, ordinary galaxies wearing the mask of ancient giants. Perhaps the light astronomers were reading as the glow of 100 billion stars was coming from something else entirely. And in time, one of the 6 surrendered to exactly this kind of scrutiny. Careful follow-up observations revealed that a single member of the group was not a vast galaxy of stars at all, but a distant baby quasar. A quasar is the blazing core of a galaxy where a supermassive black hole is feeding, pouring out light not from countless stars, but from a single ferocious engine of gravity at the center. That one object had fooled the early analysis. Its brightness came from matter falling inward, not from 100 billion suns. One of the impossible six had found a conventional, if still extraordinary, explanation. But that is where the comfort ends. Because the other five did not dissolve. They held. Observation after observation, the remaining members of the group stubbornly refused to be explained away. They were not nearby galaxies in disguise. They were not single bright engines pretending to be crowds. They were, as far as anyone could determine, exactly what they had appeared to be from the very first measurement: enormous assemblies of stars, fully grown, existing at an age when the universe should not yet have been able to grow them. This distinction matters enormously because of what it does to the shape of the problem. One anomaly is a puzzle. One anomaly can be a measurement error, a trick of the light, a quasar in a galaxy's clothing. 5 anomalies, surviving every test thrown at them, are no longer a puzzle. They are a pattern. And a pattern is precisely the thing a theory is supposed to predict in advance. When it appears instead unbidden and unexplained, it signals that the theory has missed something real about the world it claims to describe. So the field found itself holding 2 facts at the same time, and refusing to release either one. The first fact was that the standard model of cosmology had been tested for decades, against the faint background glow of the early universe, against the way galaxies cluster across the sky, against the precise proportions of the lightest elements forged in the first minutes of time. It had passed those tests with a precision that is one of the quiet triumphs of human thought. The second fact was that this same magnificent, well-tested model could not account for 5 red smudges of light sitting near the beginning of everything. Both things were true. That is the part that is so difficult to sit with. It would be easier if the old model were simply broken, if it failed everywhere and could be set aside without regret. It does not fail everywhere. It succeeds almost everywhere, brilliantly, and then breaks precisely at the edge, precisely at the earliest moments, precisely where Webb has only now gained the power to look. The failure is not scattered randomly across the sky. It is concentrated at the dawn, as though the universe had kept its strangest secret in the one place we had never before been able to see. And Labbé's 6 were only the beginning of the reckoning. They were the first warning, published while the telescope was still new, before anyone had fully grasped what kind of machine had been parked 1.5 million kilometers from Earth. The team had used cautious language wherever they could. They had called these objects candidates. They had hedged as honest scientists must on what they truly were. But the central claim survived all the hedging. Something massive was sitting where nothing massive should be, and no one could say how it had arrived there in the time available. If you had stood beside Labbé in the early months of 2023 and asked him what it all meant, he would not have offered you an answer. The honest position then, and to a large degree the honest position still, was that nobody knew. The galaxies were real, the mass estimates were real, the age of the universe at which they appeared was real. What was missing was any accepted account of how all 3 could be true together. The data had outrun the theory, and the gap between them was not closing. It was widening, and widening gaps have a way of forcing a choice. For a while the discomfort could be held at arm's length. A candidate is not a confirmation. The galaxies that had first alarmed the field were photometric estimates, brightness measurements interpreted through models, and models can be wrong. Perhaps the masses had been inflated. Perhaps a hidden black hole was masquerading as ordinary starlight. Perhaps the distances themselves were mistaken, and these objects were not impossibly ancient, but merely dusty and near. Every one of those escape routes was reasonable. Every one of them offered a way back to a universe that still obeyed its own rules. All the field needed to close them off was a single object measured so thoroughly that no escape route remained. The turning point in this story is not the discovery of something stranger. It is the moment the strangeness stopped being deniable. That moment has a date. On the 16th of May, 2025, the near-infrared camera aboard the telescope captured a faint smudge of light in a patch of sky that had been photographed many times before. It was not much to look at, a small reddish point. easy to mistake for noise, easy to overlook entirely. This point, though, had been waiting in the data, and a team led by an astronomer named Rohan Naidu, working at the Massachusetts Institute of Technology, decided to find out exactly how far away it was. They did not estimate. They did not infer from color alone. They gathered the object's spectrum, the fingerprint written into its stretched light, and they read the distance directly out of the physics. What they found, they published on the 30th of January, 2026, in a paper carrying the names of Naidu, the astronomer Pascal Osh, and 44 other researchers. They gave that paper a title scientists almost never permit themselves. They called it a cosmic miracle. The object is now known as MOM-Z14. Its redshift was measured at 14.44, with an uncertainty of only 0.02 in either direction. That precision matters. This was not a guess dressed up as a measurement, but a confirmation as solid as the field knows how to make. That number, 14.44, places the galaxy as it existed only 280 million years after the beginning of everything. It surpassed the previous record holder. It became the most distant single object humanity has ever confirmed, its light reaching us across a present-day separation of 33.8 billion light-years. Consider what that confirmation did to the escape routes. It did not weaken them. It sealed them shut. It is worth pausing on why a spectrum is so unforgiving. A photometric estimate looks at how bright an object appears through a handful of broad color filters and infers a distance from the overall shape of its glow. That inference can be fooled. A dusty nearby galaxy can mimic the colors of a distant one, and the two interpretations can quarrel for years. A spectrum does not allow the quarrel. It spreads the light into its full range of wavelengths and reveals the specific features printed there by the atoms themselves. Features that shift by a precise amount as the universe stretches the light across its long journey. Read that shift, and the distance is no longer a matter of opinion, it is a measurement. When the team reported a redshift of 14.44, they were not offering a best guess among several. They were closing the case. MOM-Z14 is not merely far, it is small. Astonishingly, almost incomprehensibly small. Its light is concentrated into a region with an effective radius of about 74 parsecs, give or take 15 parsecs in one direction and 12 in the other. To translate that into something the body can feel, this entire galaxy, this whole engine of light shining across the width of the observable universe, is packed into a space roughly 1% the size of our Milky Way. Here is the part that refuses to sit quietly. Despite that tiny size, it blazes. Its ultraviolet output is so intense that by the standard astronomers use to rank brightness, it stands among the most luminous objects ever seen at such an early time. Not bright for its size, bright in absolute terms. A pinprick of a galaxy throwing out the light of something vastly larger. To grasp that compression, picture our own galaxy, the Milky Way, shrunk down to the size of a dinner plate. On that scale, MOM-Z14 would be smaller than a single coin resting at the center of it. The coin, though, would outshine the plate. Hold both pictures in your mind at once, the tiny size and the enormous output, and you begin to feel the problem the astronomers felt. The light demands a great deal of mass and energy. The size leaves almost nowhere to put it. It had not always burned this way. The light the telescope caught was not the steady glow of a galaxy in some long, stable middle age. It was a flare. In the final 5 million years before the moment we observe, MOM-Z14 had increased its rate of star formation roughly tenfold. 5 million years, set against the backdrop of cosmic time, is almost nothing. It is a held breath. We are not seeing this galaxy in a typical state. We are seeing it caught in the middle of a sudden, ferocious surge of creation, building stars at a furious pace, just as its ancient light set out toward a telescope that would not exist for more than 13 billion years. This is the point where a stubborn intuition needs to be taken apart. Ask most people to picture the universe a few 100 million years after the Big Bang, and they will imagine something primitive. A thin, dark, simple place. A cosmos of nothing but hydrogen and helium, the two lightest elements, drifting in the cold and waiting for the slow machinery of stars to begin. That picture is not a careless one. It is, in broad strokes, what the textbooks taught for decades. The early universe was supposed to be a place of chemical poverty, a clean slate barely written upon. The heavier elements, the carbon and the oxygen and the nitrogen that make planets and chemistry and eventually people, were supposed to accumulate slowly, forged in star after star across billions of years. That picture is wrong, not slightly wrong, wrong in a way that strikes at the timeline itself. When the team examined the light of Z14, they did not find a clean slate. They found nitrogen. Not a trace of it, not a faint contamination, but nitrogen in a quantity that outstrips carbon, a ratio of nitrogen to carbon greater than 1. In the modern universe, that particular signature is rare and strange. It is seen in only a few places, chiefly in the dense, ancient cores of globular clusters, the tightly bound swarms of old stars that orbit galaxies like ours. To find that same fingerprint stamped into a galaxy as it existed 280 million years after time began is not a minor curiosity. It is a violation of the schedule. Consider what producing that much nitrogen requires. Nitrogen is not a primordial element. It was not left over from the Big Bang. It has to be manufactured inside stars, cooked in their cores, and then returned to space when those stars age and shed their outer layers, or explode outright. That process takes generations. Stars must form, live, enrich their surroundings and die, and then new stars must gather from the enriched remains. It is a relay handed across deep time. Z14 did not have deep time. It had 280 million years. A span that sounds enormous until you remember everything it must contain. The cooling, the first light, the first collapse of gas into stars, and then enough cycles of stellar life and death to load an entire galaxy with nitrogen. The arithmetic does not balance. There simply was not enough time for the ordinary relay to run. So either the relay ran faster than physics should allow, or it ran differently. The leading suspicion is the second. The chemistry hints at stars unlike any that survive today. Stars of monstrous mass, supermassive and short-lived, burning through their fuel with a violence the modern universe no longer produces. Stars that could enrich their surroundings not over billions of years, but in a furious, compressed instant of cosmic time. This is the loophole the data forces open, and it is not a comforting one. It does not rescue the old picture. It replaces the old picture with a stranger one, in which the very first stars may have been a kind of object we have never seen and may never see, because that age of giants ended long before any instrument existed to witness it. Then there is the matter of how common this is. A single freakish galaxy could be set aside as a fluke, a 1 in a trillion accident of cosmic luck. The universe is vast, and vast samples throw off outliers. Z14, however, is not standing alone. According to the same discovery paper, objects of this kind appear to be more than 100 times more abundant than the leading models predicted they should be. Not twice as many, not 10 times as many, more than 100-fold beyond what the best theory of cosmic structure allowed. This is the difference between a single surprising guest and a crowd that should not exist at all. One miracle can be tolerated. 100 miracles where the equations forbade even one is no longer a miracle. It is a sign that the equations are missing something fundamental. The man who led the work chose his words with care. It looks nothing like what we predicted, Rohan Naidu said, which is both challenging and exciting. A great deal is packed into that small sentence. Challenging and exciting are not opposites here. They are two faces of the same fact. The thing that threatens a theory is the very thing that promises a new one. To stand at that boundary is to feel the floor giving way and a door swinging open in the same instant. That double sensation, the vertigo and the wonder arriving together, is the exact texture of this moment in cosmology. Consider what the telescope actually saw. MOM-Z14 is small, not small in the way a dwarf galaxy is small. A faint smudge of a few thousand stars drifting at the edge of a larger system. Small in a way that should be impossible for something so bright. Its effective radius is only 74 parsecs, give or take a dozen. That is roughly 1% the size of the Milky Way. The galaxy you live in spans 100,000 light-years from one edge to the other. This newborn object packs a comparable blaze of starlight into a region you could cross in a few hundred years at the speed of light. Hold those two facts side by side. Enormous brightness. Almost no room to hold it. This is the disturbing reality of the early universe as Webb reveals it. The light is real. Astronomers measure its ultraviolet output and write the number as -20.2, a figure that places MOM-Z14 among the most luminous objects ever seen at such a distance. A galaxy that young should be dim. It should be a faint scattering of first stars, barely assembled, barely glowing. Instead it shines like something that has been building itself for 1 billion years, and it does this while occupying a volume so compact that the stars inside it must be crowded together at densities the modern universe has almost entirely abandoned. The brightness is strange. The chemistry is stranger. When astronomers split the galaxy's light into its component colors, they found a fingerprint written in the wavelengths. Not iron, not the heavy, slow-cooked elements that take generations of stars to forge. They found nitrogen, and not a trace of it. Not the faint signature you might expect from a universe still in its chemical infancy. They found nitrogen in startling abundance, with a nitrogen-to-carbon ratio greater than 1. In the chemistry of stars, that ratio is a kind of clock. Carbon is easy. Carbon comes early and comes cheaply. Nitrogen in this proportion is supposed to take time, many cycles of stellar birth and death, the slow enrichment of gas across hundreds of millions of years. MOM-Z14 did not have hundreds of millions of years. It had, at most, 280 million from the beginning of everything, and for most of that span the universe held no stars at all. Here is the problem. There was not enough time. Not enough time for conventional stars to live their lives, exhaust their fuel, collapse, explode, and seed the next generation with the elements measured in that spectrum. The clock and the chemistry do not agree. Something produced that nitrogen far faster than the ordinary machinery of stellar evolution permits. The only pattern in the known universe that resembles it appears not in galaxies at all, but in the ancient cores of globular clusters, those dense spherical swarms of the oldest stars, orbiting our own galaxy like relics from a vanished age. To find that same chemical signature stamped across an entire luminous galaxy, 280 million years after the Big Bang, is to find a fingerprint that should not exist on a surface that should not be able to hold it. So astronomers reach for the only explanation that fits. Not ordinary stars, but stars unlike anything alive today. Supermassive stars, objects hundreds or thousands of times the mass of our Sun, burning so hot and so fast that they could flood their surroundings with heavy elements in a geological instant before tearing themselves apart. Stars that the modern universe no longer builds. Stars that may have existed only in that first brief window when the gas was pristine and the conditions were extreme, and then disappeared forever from the cosmic record. If they were real, they would be among the first things that ever shone, and they would have lived and died before the universe was old enough to have a memory. Now stack one more impossibility onto the pile. In its final 5 million years before the moment Webb captured it, MOM-Z14 was not coasting. It was erupting. Its rate of star formation surged by roughly a factor of 10, a sudden violent acceleration in the manufacture of new stars. 5 million years, on the scale of cosmic time, is the blink of an eye. The galaxy was not slowly assembling itself across a long, quiet dawn. It was detonating into existence, building stars at a furious pace, in a body smaller than a single arm of our own galaxy, glowing brighter than nearly anything around it, salted with elements that should have taken ages to appear. And this is the moment the pivot turns all the way over. Because the temptation, when you encounter one object like this, is to file it away as a freak, a statistical accident, the one strange galaxy in a sky full of ordinary ones. That is the comfortable interpretation, and for a single object it might even be correct. But MOMZ14 is not a single object. The discovery paper makes a far more unsettling claim. Sources like this one appear to be more than 100 times more abundant than the consensus models predicted before Webb opened its eye. Not rarer than expected, not exactly as expected. More than 100-fold more common than the best theory of cosmic structure allowed. This distinction matters enormously. A single anomaly is a puzzle. 100-fold excess is a verdict. One impossible galaxy can be explained away as a fluke of observation, a misread spectrum, a trick of the light. A whole population of impossible galaxies, crowding the early universe in numbers the equations forbade, cannot be a fluke. It is the theory itself that is being measured and found wanting. The standard model of cosmology, the framework that has guided nearly every prediction about how structure grew from the smooth aftermath of the Big Bang, did not merely fail to anticipate MOMZ14, it failed to anticipate the entire crowd that MOMZ14 belongs to. And so the title of the paper begins to read less like poetry and more like a confession. A cosmic miracle. Scientists do not reach for the word miracle lightly. They are trained, by temperament and by profession, to distrust it. A miracle, in the strict sense, is an event the rules do not allow. When 46 astronomers attach that word to a measurement and publish it in a serious journal, they are not expressing joy. They are admitting that the rules, as currently written, do not permit what the telescope plainly shows. The word is not celebration. It is a flag planted at the edge of the known, marking the place where the map runs out. This is what it means to stand at the pivot. Everything that came before, the launch, the mirror, the long cold vigil at the second Lagrange point, the patient stretching of light into distance, all of it was prologue to a single uncomfortable realization. We built an instrument to confirm our picture of the early universe. We pointed it at the dawn of everything, expecting to see the gentle, gradual assembly our theories described, and the dawn looked back at us with a face we did not recognize. And the strangest part is that these impossible galaxies are not even the hardest thing Webb has found. They are massive, and luminous, and chemically premature, and they shatter the timeline. But at least we can name them. At least we know what a galaxy is. There are other things hiding in those early frames, smaller and redder and far more baffling, that we cannot name at all. They arrived without a name. In the summer of 2022, when Webb released its very first deep images to the world, astronomers began combing through the data the way prospectors comb through river silt, searching for the faint glint of something distant. Scattered across those frames, in field after field, they kept noticing the same strange thing. Tiny points of light, impossibly compact, glowing a deep and uniform red. Not the red of a dying star, not the red of glowing dust. A red unlike anything in the existing catalogues, attached to objects so small and so far that no instrument before Webb had ever resolved them at all. At first they were curiosities, a handful of oddities in the corner of an image, easy to dismiss as artifacts or noise. As more fields were imaged and more surveys completed, the curiosities multiplied into a population. Dozens of them. Then hundreds. They appeared at redshifts greater than 5, which means the light Webb gathered from them had left its source when the universe was less than 1 billion years old. They were everywhere in the early cosmos, sprinkled through the deep frames like seeds, and yet they corresponded to nothing anyone had predicted, nothing anyone had modelled, nothing in the entire library of known astronomical objects. Someone called them little red dots. The name stuck because it was honest. It described exactly what could be seen and claimed nothing that could not. Not a galaxy, because no one was certain they were galaxies. Not a quasar, because they did not behave like quasars. Just little red dots. A placeholder name for a placeholder understanding. A label that admitted the truth. We were looking at something, and we did not know what. By the summer of 2023, the trickle of observations had become a flood of papers, and a strange consensus began to form. Not a consensus about what the little red dots were, a consensus about what they shared. 3 traits appeared again and again, across object after object, in survey after survey. The first was their size. They were extraordinarily compact, far smaller than any ordinary galaxy. The second was the shape of their light when spread into a spectrum, a distinctive profile astronomers described as V-shaped, faint in the middle wavelengths and rising toward both ends. The third was the signature of hydrogen moving at tremendous speed, gas whirling inside them at velocities that hinted at something massive and violent hidden at their centers. To grasp how small these objects are, you have to set aside everything your intuition tells you about how a galaxy should look. A typical little red dot has a radius of roughly 500 light-years. Some are smaller still, under 150 light-years from center to edge. That sounds enormous, and by any human measure it is. Our own Milky Way, though, stretches across roughly 100,000 light-years. These objects are tiny by comparison, 100 to 1,000 times more compact, and yet they shine with the brightness of something vastly larger. Consider what this means. You are looking at an object barely the size of a small star cluster, glowing with the output of an entire galaxy. This is where the trouble truly begins. There are only 2 ways to explain that much light pouring out of that little space, and each of them breaks something we believed we understood. The first possibility is that every little red dot hides a supermassive black hole at its heart, feeding furiously, blazing as it devours the matter around it. The second possibility is that the light comes from stars, vast numbers of them, packed into an almost unimaginably small volume. Neither answer brings comfort. Each one, followed honestly to its conclusion, leads somewhere the standard picture of the cosmos simply does not allow. Follow the first path. If a little red dot is powered by a black hole, the mathematics demand a monster. The black holes implied would weigh anywhere from a few million to a few 100 million times the mass of our Sun. That alone would be remarkable so early in cosmic history. The stranger part comes next. In some of these objects, the black hole would account for as much as 40% of the total stellar mass of its host. Sit with that number for a moment. In the modern universe, a galaxy's central black hole is a rounding error, a tiny fraction of a single percent of everything around it. Here in the deep past, the black hole would be nearly half the entire system, not a seed at the center, not a heavy heart, something closer to a black hole wearing a thin coat of stars. Now follow the second path, and it offers no relief. If the light comes from stars rather than a black hole, then the packing required defies comprehension. To generate that much brightness in that little room, you would need roughly 1 million stars crammed into a sphere with a radius of only 4.24 light-years. 4.24 light-years is the distance from our Sun to its nearest stellar neighbor. It is a gap our fastest spacecraft would take tens of thousands of years to cross. In our quiet corner of the galaxy, that volume of space contains exactly one other star. In a little red dot, that same volume would have to hold 1 million. Not 1,000, not 10,000, not 100,000. 1 million suns, shoulder to shoulder, in a space we picture as holding almost nothing at all. To feel how alien that density is, picture the night sky as you know it. On a clear night, far from city light, you might see a few thousand stars scattered from horizon to horizon, each one separated from its neighbors by light years of empty black. That emptiness is the normal condition of space. It is what the universe is mostly made of. The interior of a little red dot would erase that emptiness entirely. Imagine every star you have ever seen, and 1,000 skies more, compressed into the gap between our Sun and the next nearest sun. The night would not be a scattering of points. It would be a wall of light, a a furnace with no gaps, a sky that never went dark in any direction. This is the kind of object the early universe apparently built with ease, and the kind it has not built since. Then comes the detail that turns a puzzle into something closer to a haunting. The little red dots are not here anymore. They fill the early universe, abundant and unmistakable in the deep frames Webb returns, scattered across the first billion years like a recurring motif. Yet when astronomers turn to the universe around us now, to the galaxies of the recent cosmos, the little red dots are gone. Not rare, not faded, gone. No population of objects in the modern universe matches them, no obvious descendants, no aged survivors carrying their signature forward through time. Something was extraordinarily common when the universe was young, and then it vanished so completely that it left no clear trace in the cosmos we inhabit. Think about what disappearance means on this scale. A star can die, a galaxy can merge with another and lose its shape. These are ordinary endings, and we can trace them. The little red dots offer no such ending. They do not seem to have collapsed into something we recognize. They do not seem to have scattered into the galaxies we map today. They were here, in great numbers, and then the record simply goes quiet, as though an entire chapter of cosmic history were torn out and the remaining pages stitched back together so smoothly that the seam is almost invisible. We notice the seam only because Webb finally gave us a sharp enough eye to read the older pages at all. This is the part that everyday experience cannot prepare you for. We are accustomed to thinking of the universe as permanent, its furniture fixed, its categories stable. The stars we see are the stars there have always been. The galaxies are the galaxies. The deep frames tell a different story. They reveal an entire class of object, common enough to appear again and again, that existed for a window of cosmic time and then disappeared. Whatever the little red dots were, they were a phase the universe moved through and then left behind, like a stage of growth that has no equivalent in the adult. We are not looking at the cosmos as it is. We are looking at the cosmos in a form it will never take again. A few clues have surfaced, though each one seems to deepen the mystery rather than dissolve it. One candidate object, catalogued as Glimpse 17775, shows signs of being something astronomers have begun to call a black hole star. The idea is as strange as the name. A supermassive black hole, feeding ravenously, wrapped inside a dense cloud of partially ionized gas so thick that the whole structure glows almost like a single enormous star. If that is what the little red dots are, they would be a kind of object the universe stopped making long ago, a transitional form between raw collapse and the galaxies we know. Here, though, the evidence turns against the simplest story. If these objects truly harbour black holes feeding at full fury, they should blaze in X-rays, the telltale scream of matter heated to extremes as it spirals inward. Most little red dots emit no detectable X-rays at all. The signature that should be loudest is silent. So the dilemma closes around itself. If they are black holes, they are too large, too early, and too quiet. If they are stars, they are too many, too tight, and too bright. Every door we open leads back into the same locked room. 4 years after the first little red dots appeared in Webb's earliest frames, 4 years of telescopes and spectra and the patient labour of hundreds of researchers, their nature remains genuinely unknown. New papers arrive, by one account, on an almost daily basis, each one announcing a solution, each one quietly unsettled by the next. The universe handed us a riddle written in a language we have not finished learning, and it did so casually, in the corner of an image, in the first week it let us look. Consider, too, what this absence does to the story we tell about ourselves. Every model of how galaxies grow, every simulation of how the first structures assembled, was built before these objects existed in our data. The models did not predict them. The models did not forbid them either. The models were simply silent, because the people who wrote them had never seen the early universe with eyes this sharp. Now the little red dots sit in the record, hundreds of them, a population without a parent and without a child. And the theories must somehow be stretched to accommodate a thing they never imagined. This is not a small correction at the edge of a graph. It is a gap in the middle of the picture, in the very era when the universe was supposed to be at its simplest. Consider the two answers astronomers have managed to offer, and notice that both of them only deepen the trouble. The first answer says the little red dots are galaxies, ordinary in kind, but extraordinary in concentration. Whole cities of stars, crushed into almost nothing. To produce the light we measure, such a galaxy would need to pack roughly 1 million stars into a sphere only 4¼ light years across in radius. That is a density beyond anything in the sky we know. Not the crowded core of a globular cluster, not the dense heart of a galaxy's central bulge, not even the suffocating crush of stars near a galactic nucleus. 1 million suns folded into a volume that, anywhere in our own corner of the galaxy, would hold little more than emptiness. The second answer says, the little red dots are not mostly stars at all. They are black holes, feeding a single supermassive object at the center of each, ranging from a few million times the mass of our Sun to a few 100 million times its mass, swallowing matter and glowing red through the dust of its own appetite. This is the more comfortable answer in a way, because we know black holes exist, and we know they grow. But the comfort dissolves the moment you weigh the numbers. In some of these objects, the black hole would account for as much as 40% of all the mass the galaxy contains. Not a fraction of a percent, the way it works in the universe we live in. Not 1,000th, not 100th, nearly half of everything. Here the riddle tightens rather than loosens. A black hole feeding fast enough to shine this brightly should announce itself in X-rays, the high-energy scream of matter heated to ruin as it spirals inward. That signal is one of the most reliable fingerprints in all of astronomy. Yet when telescopes look for it, most of the little red dots are silent. No X-rays. Or almost none. A furnace bright enough to rival 100 million suns, and in the one wavelength where its fire should be loudest, nothing comes back at all. There are exceptions, and they are stranger still. One object, catalogued as Glimpse 17,775, carries the signature of what some astronomers have begun to call a black hole star. Not a star in the ordinary sense, with fusion burning at its heart, but a ravenously feeding supermassive black hole wrapped inside a dense cocoon of partially ionized gas, so thick that the whole structure mimics the glow of a single enormous star. The light we see is not the black hole itself, it is the shroud around it, lit from within by the thing it hides. Then there is the question that returns, again and again, and refuses to be settled. Where did they go? The little red dots crowd the early universe. They are common in the first billion years, common enough that hundreds of them already sit in our catalogues. And then, as the cosmos ages, they thin and fade and disappear. In the universe around us now, the mature and settled universe of the present day, there is no detectable counterpart. None. A population that was once everywhere is suddenly nowhere, and the road between the two is invisible to us. This is what it means to find a thing that does not survive. Not that it died in some single catastrophe we could point to and name. Not that it migrated somewhere we have simply failed to search. Not that it dimmed below our threshold and waits to be recovered by a sharper eye. The little red dots appear to have transformed into something else entirely, or dispersed, or collapsed, leaving behind no clear descendant we can identify. Whatever they were a chapter the universe wrote once, in its opening pages, and never returned to. Everyday experience offers no preparation for this. On the scale of a human life, things persist. A mountain stands. A coastline holds its shape across a lifetime. The objects around us feel permanent because we watch them for so short a time. But stretch the clock to the length the universe actually keeps, across billions of years, and permanence becomes the illusion, and transformation becomes the rule. The little red dots are a lesson in that deeper grammar. They are proof that the cosmos contains entire categories of object that exist for a season, and then are gone. The inventory of what is real is not fixed. It flows. The night sky we study so carefully is a single frozen frame cut from a film almost incomprehensibly long. 4 years have now passed since the first of these objects surfaced in Webb's earliest images. 4 years of some of the most capable minds on the planet turning the problem over, publishing, retracting, refining. New explanations arrive at a pace one observer described as nearly daily, each one promising to close the case, each one quietly failing to. The shared traits remain stubbornly fixed. The compact size, sometimes smaller than 150 light-years across. The strange spectrum that brightens at both ends like the letter V. The signature of hydrogen moving at tremendous speed. The facts are agreed upon. It is only the meaning that keeps slipping away. This is the texture of the deeper trouble Webb has uncovered. Not a single anomaly we might isolate and explain in time, but a widening field of them. The impossibly massive galaxies. The premature oxygen forged in stars that should not yet have lived and died. The luminous miracle hovering at the very edge of the observable. And now these vanished red embers, a population with no parent above them in time, and no air below them. Each one alone might be absorbed, accounted for, folded back into the theory with enough patience and enough effort. Taken together, they begin to look less like a collection of separate puzzles and more like a single accumulating verdict. The pattern is not in any one measurement. The pattern is in how many of them point the same way, and what they point toward is the quiet, unwelcome possibility that something in the foundation, the part of the story we believed we understood most completely, may simply not be true. And there is one more place where the foundation has begun to crack. This last fracture does not lie out at the edge of the observable, among the galaxies that arrived too early and grew too large. It lies much closer to home. It runs straight through the single most basic number we have ever tried to measure about the universe. The number that tells us how fast the whole of space is expanding. For generations we have known that the cosmos is growing. Galaxies drift apart. The space between them stretches. The rate of that stretching can be written as a single value, a constant that governs the expansion of everything. It is one of the most important numbers in all of science. We still cannot agree on what it is. Here is the problem. We have two completely independent ways of measuring that expansion. Two separate methods, built on different evidence, relying on different assumptions, carried out by different teams. The first method works close to home, in what you might call our cosmic backyard. Astronomers build a ladder of distances using a special kind of pulsing star called a Cepheid, whose rhythm of brightening and dimming reveals exactly how far away it sits. They combine those stars with a particular kind of exploding star, the Type 1a supernova, which always detonates with very nearly the same brilliance, a dependable cosmic mile marker. Step by careful step, this ladder measures how quickly the nearby galaxies are receding from us. The team that has refined this nearby measurement for years arrives at an answer of roughly 73.17 kilometers per second per megaparsec, with an uncertainty of less than 1. The second method reaches in the opposite direction, not toward the nearby galaxies, but toward the very beginning of time. It reads the faint afterglow of the Big Bang itself, the cosmic microwave background, the oldest light in all of existence, mapped in exquisite detail by the Planck satellite. From that ancient light, and from the standard model of cosmology, scientists calculate what the expansion rate ought to be. Their answer is roughly 67 to 68 kilometers per second per megaparsec. Two numbers. 73 from the nearby universe, 67 from the ancient one. They do not match. At first glance, the gap looks almost trivial, a difference of about 6. In ordinary life, 6 against 70 is the kind of discrepancy you would round away without a second thought. This is not ordinary life, and these are not ordinary measurements. Each number has been refined to a precision so extreme that the gap between them cannot be waved away as sloppiness or noise. The two methods are each so certain of themselves that their certainties have collided. When two careful answers to the same question refuse to meet, one of two things must be true. Either someone has made a mistake that nobody can find, or the framework that connects the early universe to the present one is missing something fundamental. This disagreement has a name. Astronomers call it the Hubble tension. It has been growing, quietly and relentlessly, for more than a decade. When the first detailed results from the Planck satellite arrived in 2013, the gap was small, a faint disagreement of perhaps 2 to 3 sigma. Sigma is the language physicists use to describe how confident they are that a result is real rather than an accident of chance. A result at 2 or 3 sigma is interesting, worth watching, but easy to dismiss as a fluke that better data will erase. So that is what most people expected. They expected the tension to shrink as the measurements improved. It did the opposite. By December of 2021, the gap had grown past 5 sigma. By 2024, it stood somewhere between 5 and 6 sigma, with one study placing it at 5.8. To understand why those numbers matter, consider what 5 sigma means to a physicist. It is the threshold. It is the level of certainty the entire field has agreed upon before anyone is permitted to use the word discovery. Crossing 5 sigma does not mean a result is merely likely. It means the probability that it is a random accident has shrunk to almost nothing. The Hubble tension has not merely crossed that line. It has sailed past it, year after year, growing more certain precisely as the instruments grew more precise. This is the opposite of how errors behave. Errors fade under scrutiny. This grew under it. Now consider the hope that remained. For years there was a comforting escape route, a way to make the whole problem vanish. Perhaps the nearby measurement was simply wrong. Perhaps those Cepheid stars, the foundation of the local distance ladder, were not as reliable as they seemed. The worry was specific and reasonable. Cepheids in distant galaxies sit in crowded fields, surrounded by countless other stars. Through a telescope, that crowding could blur together, contaminating the light of each Cepheid with the glow of its neighbours, making the stars appear brighter, and therefore closer than they truly were. If that were happening, the local expansion rate would come out too high, the tension would be an illusion, the crisis would dissolve, the standard model would survive intact. This was not a fringe complaint. It was the single most plausible way out, and it deserved a real test. So the test was carried out. The instrument chosen to carry it out was the James Webb Space Telescope. On the 6th of February, 2024, a paper appeared in the astrophysical journal Letters, led by the astronomer Adam Riess of Johns Hopkins University in Baltimore. Riess had spent much of his career on this very number, and he understood exactly what was at stake. The question was simple to state and brutal to answer. Were the Cepheids lying? Webb was the ideal tool to find out, because its vision in the infrared is sharper than anything that came before it. Where older telescopes saw a crowded smear, Webb could separate the individual stars, pulling each Cepheid cleanly out of its neighbourhood and measuring its true brightness without contamination. The campaign was vast. Webb observed more than 1,000 Cepheid stars, spread across 5 host galaxies, galaxies chosen because they contained 8 of those reliable Type 1a supernovae. The most distant of them was a galaxy catalogued as NGC 5468, sitting some 130 million light-years away. Across that entire span, Webb measured the Cepheids with a clarity the crowding objection simply could not survive. The result was decisive. The fear that crowded starlight had corrupted the measurements was ruled out at a confidence of 8 sigma, not reduced, not weakened, eliminated at a level of certainty even higher than the tension it was meant to explain away. And this is the part that turns hope into something colder. The escape route was real. It was reasonable. It was the door everyone had been quietly counting on. Webb walked up to that door and sealed it shut. The local measurement was not wrong. The Cepheids had been telling the truth all along. The exploding stars had been telling the truth. The two numbers genuinely disagree, and no measurement error stands between them. Adam Rees put the consequence into words with a striking and unsettling calm. With the measurement errors negated, he said, what remains is the real and exciting possibility that we have misunderstood the universe. Sit with that sentence for a moment. It does not come from a mystic or a poet. It comes from one of the most careful observational astronomers alive. What he is saying in the plainest possible terms is that the most likely remaining explanation for the Hubble tension is not a flaw in the data. It is a flaw in our understanding of reality itself. The numbers are correct. The story that is supposed to connect them is not. This is what makes the Hubble tension so much more than an isolated argument about a single number. It does not stand alone. Step back and look at everything Webb has shown us, and a pattern emerges that is difficult to ignore. Out at the edge of the observable universe, the telescope keeps finding galaxies that are too massive, too mature, too chemically rich for the age at which we see them. Sources resembling that luminous miracle near the very beginning appear to be more than 100 times more abundant than the standard model ever predicted. Not slightly more common, more than 100-fold more common. Here, close to home, that same standard model cannot make its two ends meet on the simplest question of all, the speed at which space expands. These are not two separate crises, they may be two symptoms of the same illness. The standard model of cosmology, the framework astronomers call lambda CDM, has been the bedrock of the field for decades, predicting the large-scale structure of the cosmos with remarkable accuracy. But it now finds itself surrounded. It cannot easily explain how galaxies grew so massive so quickly. It cannot easily explain the premature oxygen, the evidence that whole generations of stars had already lived and died within the first 290 million years of time. It cannot explain why the early universe seems to have flooded space with far too much ultraviolet light, a separate puzzle that astronomers have begun to call the reionization crisis in its own right. It cannot reconcile the expansion rate measured here with the expansion rate written into the ancient light of the beginning. Each of these problems was supposed to be temporary. Each was supposed to dissolve with better data. Instead, the better the data became, the worse the problems grew. There is a phrase that physicists use carefully, almost reluctantly, because it carries so much weight: new physics. It means that the equations themselves, the rules we believed governed everything, are incomplete. It means that somewhere in the foundation there is a piece we have never seen, a force or a substance or a principle hiding in plain sight, quietly shaping the cosmos while we wrote our confident theories around the empty space where it should have been. For most of the past century, suggesting that the standard model was broken would have marked you as careless. Today, some astrophysicists use the word crisis without flinching, not as hyperbole, as a sober description of where the evidence has led. Stranger still is the texture of all this. There is no single catastrophic failure, no one measurement that shatters everything at once. There is only this slow, patient accumulation. A galaxy here that should not exist, a number there that will not reconcile, a population of red embers that flares into being and then vanishes with no explanation. Taken one at a time, each could be set aside. Taken together, they describe a universe that does not behave the way our finest theory insists it must. Consider the deepest of these cracks. It does not concern any single distant galaxy. It concerns the rate at which the entire universe is flying apart. There are two ways to measure that rate, and for years now they have stubbornly refused to agree. One method looks outward into the nearby cosmos, tracking the steady pulse of certain bright stars and the flash of a particular kind of exploding sun in galaxies we can see clearly, and from those beacons it calculates how fast space is stretching today, arriving at a figure of roughly 73 kilometers per second for every megaparsec of distance. The other method listens instead to the faint afterglow of the Big Bang, the oldest light that exists, and uses the infant universe to predict what that same expansion rate ought to be, arriving at roughly 67. Two numbers, one universe. These figures should be identical. They describe the same expanding space, measured from opposite ends of cosmic time, and a healthy theory would deliver the same answer from both directions. Yet the gap between them has refused to close. Astronomers gave the disagreement a name. They call it the Hubble tension, and for more than a decade it has grown quietly more severe. When the discrepancy first surfaced, after the early results from the Planck satellite around 2013, it measured only 2 or 3 sigma, a level easily blamed on some hidden flaw in the instruments. Not a crisis. A puzzle. But the gap did not shrink as the measurements sharpened. It widened. By December of 2021 it had pushed past 5 sigma, the threshold physicists treat as the boundary between a fluke and a genuine discovery. One careful study placed it at 5.8 sigma. The chance of that being mere coincidence is smaller than winning a national lottery several times in a row. For a while there was hope that the new telescope would simply make the whole problem disappear. The reasoning was reasonable enough. Perhaps the nearby measurement was the one at fault, contaminated by crowded fields where overlapping stars blurred together and tricked older instruments into reading the wrong brightness. If Webb's sharper vision could separate those tangled fields, the troublesome number might fall, and the two measurements might quietly slide back into agreement. In a study published in February of 2024, a team led by Adam Ries of Johns Hopkins University put exactly that hope to the test. They observed more than 1,000 pulsing Cepheid stars spread across 5 host galaxies. Galaxies that between them held 8 exploded suns of the precise kind used as cosmic measuring rods, reaching out as far as a galaxy roughly 130 million light-years away. The crowded fields were untangled. The possibility of error was ruled out at a confidence of 8 sigma, and the stubborn number did not move at all. The hope did not survive contact with the data. Ries described what remained with unsettling clarity. With the measurement errors negated, he said, what is left is the real and exciting possibility that we have misunderstood the universe. Read that slowly. Not a flaw in the telescopes, not a mistake in the arithmetic, a flaw somewhere in the understanding itself, in the picture of reality we had grown so confident about. Consider what that admission costs. For most of a century, the standard model of cosmology has been one of the great triumphs of the human mind, a framework so successful that it predicted the temperature of the leftover heat from the birth of the universe to a fraction of a degree. To stand inside that triumph and say, calmly, that something foundational may be wrong, is not a small thing. It is the sound of a science being honest about the limits of its own map. The expansion rate is only one front in this widening war. There is another. The same early galaxies that should not be so massive or so chemically mature are also flooding the young cosmos with far too much ultraviolet light, pouring radiation into the thin gas between galaxies at a pace the standard story of how the universe first turned transparent cannot account for. A review published in 2024 gave this failure its own grim name, the reionization crisis. It is a separate problem, on a separate frontier, pointing in the same uncomfortable direction. Lay the failures side by side, and a pattern emerges that becomes harder to dismiss than any single piece of it. The standard model cannot explain galaxies grown too massive too early. It cannot explain chemistry too rich and too complex within the first 300 million years. It cannot explain objects more than 100 times more abundant than every prediction permitted. It cannot reconcile the two great measurements of how fast all of creation is rushing apart. These are not 4 unrelated problems waiting for 4 unrelated repairs. They may be 4 symptoms of a single thing we have simply never seen. And here is the strange comfort folded inside the dread. A theory that fails is not a catastrophe, it is an invitation. Nearly every revolution in our picture of the cosmos began precisely here, with stubborn measurements that would not behave, with a gap that would not close, with respected scientists forced to admit that the equations no longer match the sky. The cracks are not the end of understanding, they are the narrow opening through which the next understanding will arrive, yet that door has not yet swung open. We can now measure the discrepancies with breathtaking precision. We can state the exact size of our own ignorance to several decimal places. What we still cannot do is name the thing waiting on the other side, and so we find ourselves standing at the edge of nearly everything we believed we knew, holding a map that no longer matches the land it claims to describe, looking outward into a cosmos that has just told us, in the clearest language it possesses, that the ground beneath our certainty was never as solid as it seemed. There is something worth resting inside that image for a moment, a map that no longer matches the land it claims to describe. Because the map was never the universe, the map was only ever us. Every equation we have written, every model of how galaxies assemble and how light stretches across expanding space, every careful prediction of what the first 300 million years after the Big Bang should and should not contain, is a structure built inside the human mind and then projected outward onto a cosmos that turned for billions of years before any mind existed to describe it. The universe never promised to be comprehensible. It signed no agreement to behave the way our mathematics insists it must. And so when the great telescope at the second Lagrange point returns the image of a galaxy that should not be there, a galaxy burning fiercely only 280 million years after the beginning, sitting more than 33 billion light years away in proper distance, the failure is not the cosmos failing. It is ours. The universe is doing precisely what it has always done. We are the ones who guessed wrong. And there is a strange dignity in guessing wrong this precisely. Consider what it actually took to be wrong in this particular way. It took a 6.5-meter mirror flown 1.5 million kilometers from Earth. It took 18 segments of gold-plated beryllium, folded like origami and unfolded in the dark. It took a machine chilled below 50 Kelvin, so that its own faint warmth would not drown the ancient light it was built to gather. We did not stumble into this error. We engineered our way to the exact edge of our understanding, and then looked past it, and what we saw refused to fit. That is not the failure of an ignorant species. That is the achievement of a species that has learnt to measure its own ignorance to several decimal places. Not a vague unease, not a hand-waving sense that something might be off. A precise, quantified, published account of exactly where our picture of reality breaks. So what do we do with that? What is the right way to stand at the edge of nearly everything we believed and feel the ground shift? Perhaps the answer is that this is a triumph wearing the mask of a crisis. Perhaps every contradiction the telescope has handed us, the impossibly massive galaxies, the chemistry that arrived too soon, the little red dots that bloomed and then vanished from the cosmos entirely, the sources more than 100 times more abundant than any model allowed. Perhaps all of it is the signature of a discovery still hidden just beyond the next observation, and we are the fortunate generation standing closest to the door. Or perhaps the lesson is quieter and harder than that. Perhaps the lesson is that the universe was never obligated to be the size of a human theory, and that every map we will ever draw, no matter how refined, will always be smaller than the territory it tries to hold. Perhaps comprehension itself is the thing we keep mistaking for completion. Both of these can be true at once. That is the part our instincts resist. We are built to want resolution, to want the tension to collapse cleanly into one answer, the way a held breath finally releases. But the cosmos offers no such collapse. It holds both possibilities open, the triumph and the humility, the door and the wall, and it asks us to carry them together without forcing either one to win. This is not a comfortable posture. It is, however, an honest one. And honesty about the limits of what we know has always been the most reliable engine of what we eventually discover. It is worth noticing how the scientists themselves chose to speak in these moments, not with despair, not with the language of defeat. When the team confirming the universe's stubborn expansion rate ruled out their own measurement errors at a confidence so high it left almost no room for doubt, the astronomer leading that work Adam Ries of Johns Hopkins University, did not call it a disaster. He called it the real and exciting possibility that we have misunderstood the universe. Read that sentence slowly. Misunderstanding, named openly, and called exciting in the same breath. That is not the reflex of someone who has lost something. That is the reflex of someone who has just glimpsed how much is still left to find. The same register appears again and again, from different mouths across different discoveries, when Rohan Naidu of the Massachusetts Institute of Technology described the most distant galaxy his team had confirmed, the one whose chemistry looks nothing like anything in the modern sky. He did not retreat into caution. He said it looks nothing like what we predicted, and then he chose two words to hold side by side: challenging and exciting. When Kevin Hainline at the University of Arizona tried to convey the shock of finding oxygen forged by multiple generations of dead stars inside a galaxy that had barely begun to exist, he reached not for an equation, but for a story. The image of an anthropologist uncovering an ancient city and finding, impossibly, the evidence of iPhones buried in its ruins. And when Ivo Labbé first looked at his cluster of giant infant galaxies, far too heavy for their age, he did not soften the contradiction. He simply said it. We just discovered the impossible. The impossible. Notice that none of them flinched from the word. Notice too that none of them stopped working because of it. The word was not an ending. It was a beginning dressed as an ending. This is the quiet emotional architecture beneath every great unraveling in the history of this science. The people closest to the broken theory, the ones with the most to lose from its collapse, are almost always the first to feel the thrill rather than the grief. They have spent their lives learning to read a sentence the universe is still in the middle of writing, and they understand something the rest of us forget under the weight of the dread. A wall that will not move and a door that has not yet opened are not the same thing, even when they look identical from where we are standing. And where exactly are we standing? It helps, here at the close, to remember the true dimensions of the room we are in. The observable universe stretches roughly 46.5 billion light-years in every direction we could ever point a telescope. A sphere very nearly 93 billion light-years from one edge to the other. And that is only the portion whose light has had time to reach us at all. Within that almost unimaginable volume, the most distant galaxies the Great Telescope has so far confirmed are showing us the cosmos as it looked when it was only about 2% of its present age. Sit with that fraction for a moment. 2%, which means that 98% of all the time that has elapsed since the beginning still lies further back, beyond even Webb's current reach, folded into wavelengths still too faint or too stretched for this generation of mirrors to gather. We have not reached the edge of the universe. We have reached the edge of our instrument. The territory beyond it is not empty. It is simply, for now, still dark to us. That distinction matters enormously because it changes the shape of the feeling. The dread that comes from these discoveries is not the dread of a closed cage. It is the vertigo of an open horizon. When the theory fails, it does not fail by showing us less than we expected. It fails by revealing that there is far more than we ever imagined, packed into the first few 100 million years, structured in ways our equations cannot yet account for, abundant where we predicted scarcity, complex where we predicted simplicity, present where we predicted almost nothing at all. We did not look out and find an emptiness too large to bear. We looked out and found a richness too large to explain. Those are not the same terror. One is the fear of nothing. The other is the disorientation of too much. And the most remarkable part is that none of this is finished. Not the question, and not our part in answering it. The galaxies that broke our models are not the last galaxies. The telescope that found them is not the last telescope. The scientists reading these spectra tonight, in observatory control rooms scattered across the planet, are not the last people who will ever stare into this particular dark and feel the floor tilt beneath a long-held certainty. Every contradiction the data has surfaced is now a thread, and somewhere just out of sight those threads are gathering toward an explanation that no one alive has yet written down. We can feel its pull in the precision of our confusion. We cannot yet see its face. So the question that remains is not really a question about distant galaxies at all. It never was. It is a question about what kind of creatures we choose to be when the universe tells us, in the clearest language it possesses, that we were wrong. We could meet that news with fear and close the book and decide that some knowledge is too unsettling to pursue. Or we could meet it the way the people who built this machine have met it, with that strange double register the discoveries keep demanding, the dread and the wonder held in a single steady gaze. There is no equation that decides this for us. The mathematics can tell us the size of our ignorance. It cannot tell us how to feel while standing inside it. That choice has always belonged to us, and it belongs to you, right now, lying here in the dark, listening to a story about light that left its source before the earth, the sun, or anything you have ever loved had begun to form. Perhaps the discomfort is only temporary. Perhaps a quieter theory is already taking shape in some small university office, a refinement that will fold these impossible galaxies gently back into a model that makes sense, so that a decade from now, the children of these astronomers will learn the corrected story as though it had always been obvious. Or perhaps the cracks run deeper than any patch can reach. Perhaps the standard model that has guided cosmology for a generation will simply not survive the things this telescope keeps finding, and what feels now like a crisis will be remembered instead as the first tremor of a revolution that changed the meaning of the word universe itself. Both of these futures have arrived before. The history of this science is a history of confident answers quietly replaced by stranger ones. And in every single case, the new understanding came not from the people who looked away, but from the people who kept looking. Notice what the people closest to this work actually chose. They did not reach for the language of fear. When a galaxy refused to behave, one of them called it a cosmic miracle. Another, staring at oxygen that should not yet exist, said it was like an anthropologist uncovering an ancient city and finding evidence of telephones inside it. The lead author of the most distant galaxy ever confirmed described the result, in the same breath, as both challenging and exciting. That is the register the evidence keeps demanding. Not certainty, not despair, something braver than either. Which of those futures actually arrives is not something a single measurement can settle. It is not something anyone can hand to you finished and resolved. These questions have no final answer waiting at the back of the book. Different minds will read this same evidence and reach different conclusions, and some of those minds have not yet been born. The astronomer who finally explains the little red dots may be a child tonight, somewhere on this small warm planet, looking up at a sky that has not yet told them its secret. The choice of whether to keep asking belongs to all of us, and tonight, in this very quiet hour, a small piece of it belongs to you. So let the scale settle over you one last time. You are lying on a single planet, circling a single ordinary star, inside a galaxy of several 100 billion others, adrift in an observable universe that stretches roughly 46.5 billion light years in every direction you could ever turn to look. 93 billion light years from one edge to the other, and nearly all of it lies beyond your reach forever. The galaxy we call MOMZ14 sent its light toward this place 33 billion light years ago, when the entire cosmos was barely 2% of its present age, and 98% of everything that has ever happened lies further back still, in a darkness even this magnificent machine cannot yet pierce. And yet here is the thought worth carrying down into sleep. We built an instrument that could see almost all the way to the beginning. We aimed it at the oldest light there is, and the universe answered, not with silence, but with something its own discoverers could only bring themselves to call a miracle. We were wrong about a great deal. That is not a defeat. That is the sound of a door swinging open, because the creature that can be wrong, and know that it is wrong, and lean toward the wrongness with wonder instead of fear, may be the most remarkable thing this telescope has ever found. The universe is older and stranger than we ever dreamed, and almost all of it is hidden still.